Assalamualaikum and hello everyone. So welcome back. So this is the final part for chapter 9. So in which I will use the moment area theorem that we already learned in chapter 9.4. So on the unsymmetrical loading in order to find the slope and deflection of the beam. So basically, the idea is the same. So if, let's say, you have a beam with unsymmetrical loading, so what you need to do is draw the moment diagram of this beam first. And then you need to divide it with EI in order for you to get the value of area and also the X bar. Okay, so let's say we need to find the value of theta. Okay, so theta at this point D here. Okay, what we need to do is we need to put one of the support. So in this case, so I will choose support A as our reference. Okay, so the first thing that you need to do so is finding the value of theta A. So mathematically, so we can get the value of theta A. Okay, so as the TBA over here, the length of TBA divided by value of L of the whole length beam. Okay, so the value of TBA here, okay, so is just the total value of the area time the X bar from the our moment over EI curve. Second part, okay, so for the second part, so we need to use the um, theta A in order for us to find the value of theta D. So if we were to draw the value of theta D, so we have a tangent of theta D here. Okay, and then this is the value of our theta D. Okay, and then we have the theta A, which we already calculated from this formula here. Okay, then we need to find the value of theta D divided by A, and this value is what we can find from the moment over EI curve. Okay, so we can get the value of theta D as theta A. Okay, so plus theta D over A, because this is just a mathematical expression if you do the angle calculation over here. Okay, so that is what you need to know. So in order for you to find the value of theta slope at the point in the beam here. Alright, so next we need to find the value of the deflection at point D. So the at this part, okay, so you can use this formula here. So basically, if you were to draw the triangle, so we can get a similar point in which we get a line of EF over here. So basically, so the value of EF divided by X is the same as value of BH divided by L. Okay, so then you can get the value of EF, okay, as X over L times TB over A. And the value of TB over A here, as I said before, is just the total value of area time X bar. Okay, then we need to find the value of YD, which is situated here. Okay, so we can get the value of YD as total length here. So EF minus ED, but negatively because this is going downward. So it's much easier if you calculate it as ED. Okay, so ED minus EF. All right. So to get the value of ED, so this is just TB over A. Okay, and this point here, so you can get from the AX bar. Okay, so from point D to point A. Okay, and for the EF, so we can use this equation here. So in the end, so you will get the value of your deflection as this point, this formula here. Okay, and the same thing with your theta D. All right, so it is straightforward. So all you need to know is to find your reference correctly and then use that reference to calculate the value of theta A and also value of EF over here. Okay, so let's try one example in which we can apply this formula to help us to find the slope and deflection at certain point. Alright, so let's try to solve for the theta and y at point D for the beam shown here. I think you guys is already familiar with this beam. So because previously we already solved this using other method. Okay, but first you need to solve for the reaction. So in here, so we already know the value for our reaction here is 3p over 4, and over here is 3 p over 4. Okay, and then we need to draw the moment diagram for this beam here. All right, so if you still don't remember how to draw the moment diagram, so first you need to draw the V diagram. Okay, so which is the easier. Okay, so the V diagram. So we can get the an X diagram here. Okay, so let's say so this is 3p over 4. So from 0 to 3p over 4, and it is constant until it reach L over 4 over here, and then it's going down p. So this will be p over 4 negative, and then it will constant and going up at p over 4. So this is your V diagram. Okay, and then we can draw our moment diagram. So we can draw our moment diagram just by taking the area inside this box. So let's say 3p over 4 times L over 4. So what we get is 3pl over 16. Okay, so 3pl over 16, and it reached the maximum because this is a positive, so it will be a linear line going upward, and over here the area will be p over 4 times the 3p over 4, so you will also get the 3pl over 16. Okay, so and it is going downward until it reach 0, and this is your moment diagram. Okay, and our point D is located here at point of L over 4. All right, so this is our enlarged moment diagram. So in order for us to use the formula, so we need to divide our moment diagram into M over EI diagram. Okay, so you just divided the whole thing as 3PL over 16 EI. Okay, and the shape doesn't change, only the magnitude is changing. Okay, so to make it easier, so we can divide this into two parts. So in which this triangle here, okay, so will be part 1, and the second triangle will be the second part. Okay, so for finding the theta A, so we know that the theta A is minus T B over A over L. Okay, so we need to find the value of TBA, okay, which is just the whole area times the X bar. Um, okay, so we can calculate it one by one. So we can find the value of A1, okay, is as the value of the area of this triangle here. So will be 1 over 2 times 3PL over 16EI, okay, time L over 4. Okay, and then you will get the value as 3PL square over 128 EI. Okay, then we can find the value of A2. Okay, so in which is the value of the 1 over 2 time 3PL over 16 EI2. Okay, time 3L over 4. So over here, so we will get the value as 9PL square over 128 EI. Alright, then we can further calculate the value of x1 and x2. Alright, so for x1, so we know that it is situated 1/3 from this point here. Okay, so over here is our x1. So we can draw, we can find from the right side to the point of the center here. So this is our x1. And for the x2, it is also 1/3 from the long end of the triangle. So it should be around here. Okay. So this is the value of our x2. Okay. So for x1, so the value will be, okay, so 1 over 3 times L over 4 over here. Okay, so we get 1 over 3 L over 4 plus 3L over 4. So we will get 10L over 12. Okay, and for the x2, so we need to minus 3L over 4 minus the time 2 over 3. Okay, so 3L over 4 um, time 2 over 3. So which is just 6L over 12. So this will be L over 2. Okay, so you get this value here. Okay, so from the value of A and X bar that we already find, okay, so in this moment area curve here, okay, so then we can proceed to find our theta A. So our theta A is just minus TB over A divided by L. So we can find TB over L as A1 X1 plus A2 X2. Okay, and you can just take out this value here, and you can find the value as 7PL cube over 128 EI. So our theta A, okay, so our theta A will be minus 7PL cube over 128 EI. Okay, so divided by L. Okay, so you get the final answer as 7PL square over 128 EI. So that is the value of our theta A. So now we can proceed to find the value of theta D as theta A plus theta D in reference to A. So the value here will be minus 7PL square over 128 EI. Okay, and plus theta D over A, which is just the area 1. Okay, so we can put the area 1 as 3PL square over 128 EI. Okay, so final answer for your theta D, it will be minus PL square over 32 EI. Okay, so this will be your final answer for theta A. Theta D, I mean. Alright, so next we need to find the value of YD. So in order for us to find the deflection at YD. Alright, so let's use the formula to find the value of YD. Alright, so the value of YD will be, as before this, YD is equal to DE minus EF. Okay, and to find the value of DE, so this is just the value of D over A. So basically, so we are only focusing on this triangle here. Okay, so the area is still the same, but for the X, it will be changing. So this is 1/3 from L over 4. So this will be L over 4. Okay, so our TDA is just A1, okay, time, okay, so L over 12. Okay, so L over 12. Because this is L over 4 times 1 over 3, so L over 12. So just get the value of A1 here. So you will get 3PL square over 128 EI, okay, times L over 12. So you will get the answer as PL cube over 512 EI. Okay, so that is for our DE. Then you can find the value of EF. Okay, so EF just X over L. Okay, so time T B over A. Okay, the value of TB over A. So you already found. So which is 7PL cubed over 128L. So the X is L over 4 because our D is situated here. So this will be L over 4 divided by L. Okay, so it will become 1 over 4 times 7PL cubed over 128 EI. Okay, then finally, so you can use both of these value to find your YD. So in which your YD is just DE minus EF. Okay, so if you put the value, you calculate the value, so you will get minus 3PL cube over 256 EI. Okay, and this is your final answer to for YD. So when we have a simply supported beam that is not subjected to a symmetrical loading, so we are not necessarily will get the value of our maximum deflection at the center of the beam. So in this case, so we need to determine the point where the maximum deflection occur, and we can denote that point as the point K, okay, where the tangent is horizontal. So basically when we have Y max, okay, so at Y max, so our theta will be 0. Okay, so in this case, so we can say theta K is equal to 0. Okay, so if we have that point, okay, so of theta K, so we need to find the distance of the location of the maximum deflection before we can find the Y max. So in this case, so we can use the moment area theorem by using this equation here. So if we have a theta A, okay, the one as same as one we already solved previously. So we can get theta A is equal to minus TBA over L. Then we can get the value of theta K, which is 0, is the same as theta A plus theta K over A. So basically, so our theta K in reference to A is basically is just minus theta A, right? So we can find the point K, okay, so by measuring the area under the M over EI diagram, which will be equal to value of minus theta A. And after we get the value of uh, point, the distance from A to K, then we can compute the value of Y max by taking out the value of A plus X bar. Okay, so let's try on this question again. So the same beam. So we want to find the maximum deflection of the beam. So previously, so we already solved for the value at D. So now we want to find the value of K in which the Y max is happening. So basically, so because the length of the L is slightly longer on the right side, so we can predict if we have a deflection, so the maximum deflection will occur slightly after value of D here. Okay, so let's say this is our K. And it is much easier if we take theta B as our reference in this case because it will only involve one area. So if this is our moment diagram, so that we already solved just now. Okay, so our K should be around here. Okay, and we can put this length as U from point of B. Okay, so this is A, this is B. So this is our area of interest that we need to find. Okay, by using the equation that I have shown you before. Alright, so let's try to find the value of the U or the area that is related to the k here. So because I want to choose now b as our reference, so I need to find the value of theta b. So theta b is just theta a. Okay, so plus theta b over a. Okay, so this will be the one that we already solved just now. So theta a plus theta b over a. So the whole area of a1 and a2. So a1 plus a2. So, and we already saw for the value for all of this. So you can add up the value. So you will get 5pl square over 128 ei. So that will be our theta b. Now, so we need to solve for the value of area for this part here because we need to find the value of u. Okay, so if I want to find the moment that is situated here, so because this our reaction here is P over 4 and this is length of U. Okay, so if I cut this off, so our moment here will be PU over 4. Okay, so the length here will be PU over 4 EI. Okay, and then we have the length of U. So now we can get the value of our A as 1 over 2 time U time PU over 4 EI. Okay, so our value of A will be PU square over 8 EI. Okay, so we want to find the value of U. So if we look at the equation, so we know that theta B over K, so B to K over here, is just the same as theta B minus theta K. Okay, and we know that the value of theta K is equal to 0. So theta B over K is equal to theta B, which is the value over here. Okay, and the value here can be solved by just taking out the area here. So from as our first moment area theorem, so this is equal to A. Okay, so we can solve this. So 5pl square over 128 ei is equal to pu square over 8 ei. Then we can get the value of our u as 0.559 L. So this is from this part here. So the location of K, okay, so the location of K is at so location of K is at L minus 0.559 L. So it is situated at 0.441 L. Okay, so that will be our distance from A. Alright, so since we already determined the value of U just now, alright, so since we already determined the value of U, so now we can calculate the value of Y max. Okay, so the value of Y max is equal to T over B from K in reference to K. And this is just A time X bar. Okay, so in which our X bar is situated here. So it is 2 over 3 U. Okay, so this is our X bar. Okay, so we can get the value of A, which we already solved just now. So the value will be PU square over 8 EI. Okay, so time 2 over 3 U. Okay, so this is our Y max. So we can get the final answer as PU uh, cube over 12 EI. Okay, and because our U just now is 0.559 L, so we can calculate the value of our Y max as P times 0.559 L cube over 12 EI, and this will come out to the answer as 0.01456 L cube PL cube over EI. Okay, so that is how you can find the maximum deflection of the beam. All right, so that's it. So basically, for in this video, so I have shown you how to use the moment area theorem to find the slope and deflection, and also the maximum deflection of the beam in in unsymmetrical loading. Alright, so that is the end for the chapter 9. So in this video, I already shown you how to find the slope and deflection of the beam in unsymmetrical loading, and also try to find the maximum deflection of the beam in unsymmetrical loading. Alright, so in summary, okay, so depending on the type of loading, so you can find the slope and deflection using three different methods. So if you have a very simple loading, so you can use the double integration method. But if you have the loading, which you can break it down into case shown in the appendix D, so you can use the method of superposition. And finally, if you have some complex loading or asymmetrical loading that is hard to solve, so you can use the moment area theorem. So it is all depending on what you are comfortable with, and I would suggest you to try to find try to solve the question that is in the your textbook. Okay, so that's it for chapter 9. So as usual, so if you have any question, you can contact me directly, so using the WhatsApp or email, and I will try my best to answer to you. Okay, so thank you for your attention, and good luck for your final exam. All right, thank you very much.